All right, good Tuesday morning to you. We're going to pick up where we left off. I was talking yesterday about musical instruments in the harmonic series, and we talked about how stringed instruments work. So I wanted you to recall that we came up with an equation here for all the different frequencies you would hear from a string that had been plucked. And this is the formula. It's got an indexing variable n in it. So it's n times v over 2 times the length of the string. And n is an indexing number, so it goes up through the counting numbers, 1, 2, 3, 4. That's the number of the harmonic. And remember that you normally put n equals 1 into this equation. That gives you the fundamental frequency, which is the name of the note. The lowest frequency created by the string is the one that the ear hears as the note. So let's talk about how wind instruments work. Every wind instrument is made up of some sort of tube, and the tube is full of air. So I know, you think of a trumpet as having a mouthpiece on one end, and then it curls around and does some stuff, and then there's a bell on the other end. But really, that is just a tube of air where you're making some noise with the mouthpiece at one end, and the other end is flared out to help spread the sound out, but the sound comes out the other end. So what's happening inside this tube, whether it's a trumpet or a clarinet or the muffler of your car, is that the air inside is vibrating in a standing wave. Now, this is where we need to argue about things. What are the boundary conditions? What's true at either end of this? And I submit that since sound is a pressure wave, that either end of a tube is a node. That means you cannot have any excess or deficit of pressure at either end. If there's an excess of pressure at one end, then the air molecules will simply leave. If there's a deficit of pressure at one end, then air molecules from outside will simply come inside. So we have the same boundary conditions as we did with the string. There's a node at each end, and you can have all kinds of stuff happening in the middle. So basically, the easiest and simplest wave you can have inside this tube is to have normal pressure, and I'm going to represent that as normal density of air at one end and the other end. So there's an average number of air molecules per square inch or square or cubic inch. But in the middle, you have an area that's going to go through compressions and rarefactions. So I'll draw it as being higher than normal density. So many more dots per cubic inch right there. So we have an antinode in the middle. If we want to represent this as a graph of density or pressure, we would say that there's average density at each end and that there's an increase in density in the middle. See, I've drawn this graph sideways, right? Normally we would draw a horizontal line, and things that were above would the line would be more pressure and less pressure. But because I drew this tube sideways, I'm drawing the graph sideways. This antinode would actually be bouncing back and forth between an excess of pressure and a deficit of pressure, excess of density and deficit of density. But you can see from this drawing, this graph of pressure or density, that we have the exact same situation, the geometrical situation we had before, and that is that the length of the tube is exactly equal to half of a wavelength. And that means that the wavelength is L over 2, and that when we put it in the equation, we're going to get a frequency that is going to be V over 2L. And that's going to be the fundamental frequency. And it matches exactly what we got for the string. And that's no big surprise because we have nodes at either end, just like we did with the string. However, in this case, the velocity is the speed of sound. And that's a little easier to handle than the velocity on a tight string. The length is the length of the tube, and the velocity is the speed of sound. And so what's the next most complicated thing you can do? Well, here's my tube. I got to have a node at each end. And now, instead of having one antinode in the middle, I'm going to have two antinodes. And so our first antinode is going to be a high density area, then a node, and then a low density area, and then a node right here. So this would have a graph of pressure or density that would do one of these. And I think we can see that that means that L equals lambda, and F2, if you do the math, is going to wind up being V over L. So we could continue doing this, drawing pictures of different waves that might fit, and N, we need an A and an N and an A and an N and an A. Three antinodes. No. I usually make a joke about the Batman theme song or the end of a Journey song or Hey Jude or something at this point, but it's 7:10 in the morning, so I'm not doing that. Okay, here we go. There's all the air molecules trying to draw dense, normal, not dense, normal, dense, normal kind of thing. And our graph would look like this. But those of you who have good pattern recognition are already seeing that this follows exactly what we did. Oops, that's a 3 lambda over 2. And that means that F equals 3V over 2L when you get done with the math. Um, so we're going to get the same kind of harmonic series we got before. It's just that the velocity is going to be the speed of sound. So the frequency is from an open pipe, and that's what this is called because it's open at both ends. Open, open, is going to be N times V over 2L, where N is this indexing variable. And this kind of explains why it is that wind instruments can play in the same orchestra or have the same musical structure to them as stringed instruments, because they have exactly the same set of frequencies. And that is to say that the first two, if the first one is a C, the second one is a C an octave higher, and the third one after that is a G, and then there's another C, and then there's more to come. It has the same structure. So all the things that are true about stringed instruments are true about wind instruments. Almost every wind instrument in the orchestra is an open pipe. I know I just said the trumpet had a mouthpiece at one end, but really what's going on, as I said, is that the mouthpiece is making some noise and starting a wave, and the rest of the trumpet is acting as a resonator, as an open pipe. Let's say one thing about this now that's musical, and I want to talk about the word timbre, which we threw at you earlier in the deal. But if we make a graph of all the different frequencies that come from a musical instrument versus how loud they are, the amplitude of them, we'll find that we get a set of spikes. They're equally spaced because the frequencies in the harmonic series are equally spaced, but they tend to get quieter as you go higher. But the actual structure of which ones are loud and which ones are soft, it actually contributes to the tone. So, for example, a saturated electric guitar tone might have this kind of structure where each frequency is represented but in a slowly decaying pattern. You play an oboe, you might get a lot of fundamental, almost none of the second harmonic, a whole bunch of the third harmonic, almost none of the fourth harmonic, and then maybe some fifth harmonic. So this might be a guitar sound playing a certain note, and this might be an oboe sound playing the same note. And this is what we can tell the difference in tone is called, timbre, which is spelled timbre. And that's what lets you hear with your ears and your brain the difference between different instruments. Back in the bad old 80s, when I was learning about music and stuff, there was an emphasis on synthesizers. And synthesizers were electronic instruments, no strings, no wind, but a bunch of different oscillators that would make these frequencies synthetically. And then you would actually have controls that you could set how much of each harmonic was available and make the sound different. In fact, you could have these relative amplitudes change over time and get kind of swishy sounds. If you go back even into the 50s and 60s, the Hammond organ had a mechanical system for making these frequencies, and then you had little sliders, they called them drawbars. You could pull out how much of each harmonic was going to be present in your sound. Of course, the rock and roll people just grabbed all of them and pulled them all out, making the loudest, most harmonically rich sound they could and overdriving the amplifier. And that's why Deep Purple sounds the way Deep Purple sounds. We have one more thing to do here, and that is there is such a thing as a closed pipe resonator. That is to say, a pipe that is closed on one end. So the closed pipe resonator, we're going to seal off one end here. The open end is still going to be a node, but a closed end is the opposite of a node. It has to be an antinode. This is the first time we're seeing different boundary conditions. So what's the simplest thing you can put inside of a closed pipe? Well, a node has average density, and then we're going to slowly increase in density until we get to very high density at the antinode. A graph of that density or pressure would look like this. And now the length of the pipe doesn't have half of a wave in it, it has a quarter of a wave. And if we do the math, we're going to find that lambda is 4 times L, and that means that V equals lambda F. It can be monkeyed around to be F is V over lambda. That's V over 4L. So F1 is V over 4L. This is a different frequency than the open pipe, which was V over 2L. In fact, if you have any knowledge of math, you realize that this is half as much, right? A 4 on the bottom instead of a 2 on the bottom. This is half as much. So closing the bottom of a pipe resonator will make the frequency drop in half. And you remember our terminology there was an octave. So this would be an octave lower. You can test this out. Just pull a straw out I was going to say pull a straw out of a drink you get at a fast food restaurant, but I guess you still get straws with fast food. And blow across the top, and then put your thumb over the bottom of the straw and blow across the top, and you'll see that the pitch goes down, not up. So if we continue with this, we're going to find that the next one in the series has a node, an antinode, a node, and an antinode. You always have to alternate nodes and antinodes. And this is going to be that much. And that is L equals, now how much of a wave is that? That's 3/4 of a wave. So 3 lambda over 4. And when you get done with the math, you're going to find that F2 is 3V over 4L. The next one, F3, is going to be 5V over 4L. So what's the pattern here? Well, we seem to have an odd number, 1, 3, and 5. So for the closed pipe, we need an indexing variable, and getting odd numbers is difficult, but 2n minus 1 always gets you an odd number. So 2n minus 1 times v over 4l. All right, so are there any musical instruments that have closed pipes? I don't believe there are any in the orchestra that have closed pipes, but a didgeridoo might be a closed pipe resonator, and certainly pipe organs have closed pipe resonators to make the lower frequency sounds. Does this follow the same pattern as before? Well, no, it's a different formula, but you'll notice that the difference between any two frequencies in the series is still the same size. So it may have a different starting point and a different structure, but the gaps between the frequencies are the same for a closed pipe as an open pipe. So that's the secret of music, that strings and tubes full of air have a harmonic series that's created whenever you excite waves inside of them, and it's the same for strings and pipes. And Western music and our creation of note names and the distance between different frequencies that we give notes is all based on the hidden frequencies that are inside of these things. Did it have to be this way? Could we have invented a different kind of music? Of course we could have. Certainly if we were using electronics, we could have made any structure we wanted, but this is what came out, and this is what we find pleasing with our brains. So I hope you had a chance to watch that video, the one about what's up with noises. I think it's worth watching maybe twice because that girl talks fast and doesn't seem to breathe. If you enjoyed her video at any level, she does mathematical videos, and her name is Vi Hart, V-I Hart, H-A-R-T, no relation to our teachers. And she does one on hexaflexagons, a series of them, including an edible hexaflexagon. And that hexaflexagon one really blew me away. It was a lot of fun. It was math, but it was also a craft project. And since we're all stuck inside, maybe it would be something fun for you to do, is to build a couple of hexaflexagons. All right, I've gone a little over my 12 minutes here, so we will talk later.